It's buying something.
My body. Oh, there now it is.
We have.
Mr. Gordon, in order to keep it at home.
Miss Newman is so much fun. I have a very good.
In order to hear me, hey, as soon as you start talking, conversation's got to stop. Start moving forward. For the graph, what I would recommend, is going by fives. And every time that I make a graph, I make it a point of putting 2 zeros in here. Too many times people forget that the origin is actually has 2 coordinates. It's 0, 0. So I put a little 0 over here, I put a little 0 here, but it's the same starting point. We're going up to 80 for this scientific scenario. That should be enough. Every graph's a little bit different. You have to get a feel for how you should set up your units. I decided to do by fives. The next one, I believe, the back of this is also by fives. And then the practice one that you're going to do, you'll probably just use units of 1 because the numbers are much smaller. But try to make your graph as big as possible. Today, you're only going to do one more practice problem after we go through a couple of examples. So use the entire piece of graph paper, whatever you have in front of you. Don't be afraid to use the space. For some reason, my other classes wanted to put everything in a little corner. You've been trained so often to not waste paper and to condense things. I want you to expand things so that we can see what's going on. We've got some trees that need to be planted. There's some information on your sheet regarding money. There's some information on your scenario regarding area, square feet. And then carbon dioxide absorption is also thrown in there. The first thing you should do is underline or circle what it is that you are being asked to do. What should I circle? What's being asked? How many of each tree, and then circle to maximize carbon dioxide absorption. How many of each tree? So the last thing we're going to do after we solve this entire scenario is write a sentence that actually explains your answer. That'll be the end of every problem. You don't just write down a number and move on. Give me a complete sentence explaining what you just found. Put a dividing line on the right-hand side. On the top of this, we're going to put parameters. On the bottom part, we're going to put our maximization equation. Since we are looking at 2 different trees, up above, I'm going to write let x equal and let y equal. What are the 2 types of trees?
Spruce and maple.
Number spruce trees, number maple trees. If you don't have variables in front of you, you need to declare your variables at the very beginning. Then I would take a look at what it is that you actually need to find. Since it's saying carbon dioxide, I'm going to use a capital C. let C equal carbon dioxide absorption. Since we'd only deal with 2 or 3 examples at a time in this unit, try to write out as much as you can. Give me as much detail as you can. What numbers correspond to carbon dioxide absorption? What should I be focused on when I'm creating this equation? What numbers? What? 650 and 300? What will the equation look like?
C equals 650x plus 300y.
Plus 300y, according to those variables that I declared. 650 goes with spruce, 300 goes with y. Well, we need some parameters. I see money up there. I'll go to that first. I only have $2,100, which means I could spend less. That's the maximum. So I'm going to put a less than or equal there. And it's $30 for spruce. It's $40 for maple. Does it follow that I put 30x plus 4y? Does that make sense? If it helps you to remind yourself what you're dealing with, put some dollar signs if you want. They're not really important until we get to the end. What else should I put in here? What other variable haven't I discussed yet? Space it takes up. I'm assuming that the root system of the tree needs a certain amount of square feet. What's the maximum square feet? 45,000. That's what's available. We don't have to use it all, so I'm going to put less than or equal to. And the numbers we want there would be 600 and 900. So 600x plus 900y. There are a couple of constraints or parameters that sometimes are shown, but not always. Do we want negative trees?
Yeah.
So we could say that we want x to be greater than or equal to 0, and we want y to be greater than or equal to 0. Sometimes that's included, sometimes it's not. Depends on the textbook, depends on the scenario. Sometimes you're expected to make some deductions and assumptions because you have a real life situation. If we don't plant any trees, what's the point? I don't know what a negative tree looks like. Deal with this. Pile of ash. Is that how we're going to end our Friday? What did you do? What did you do when you were doing the simple problems that I assigned you for homework?
You got 0 on the x and then got 0 on the y.
Because we were dealing with whole numbers that worked out pretty evenly, we threw in some zeros. This first 0 for x, that makes that entire term 0. What's 2100 divided by 40? How much? 52.5. So we have a decimal in here, but 0.5 isn't too hard to deal with. And if I put a 0 on that term, that effectively gets rid of that, and you're left with 30x and 2100. What would x be? 70. Plot those points. I'll put those in green. We have 0 and 52.5, which would be right about halfway between 50 and 55. And 70 and 0. 70 0. Because we're not computers, this is going to be less than accurate, but do the best that you can. Use your straight edge, big straight line. And the same is true for 600x, 900y. Because these numbers are very simple, a lot of zeros, it should be easy for me to do the same thing, throw in a couple zeros. It's 52.5. If I throw in a 0 for x, what would that y have to be? How much?
50.
50? Do a little division. 45,000 divided by 900 is 50. And if I make this 0, then I've got 45,000 divided by 675. So no decimal there. Plot those 2 points. If you have multicolored pencils, pens, this topic, this unit might be helpful to actually use those. 0 and 50. So we're right there, a little bit lower. 75 and 0 right there. Connect. And if I want to shade and see where the 2 shadings cross, can you see that there's an intersection point right around there? And if I shade below the green line, below the red line, the actual feasibility region is right here. Write that in, feasibility region. So it does not include this little space here. It does not include this space here because there's no overlap there. The green section that I made does not overlap with the red section there, and this, let's see, green, actually, is that part included?
No, because the orange isn't gold.
The orange isn't in there,
Yeah.
correct, thank you. So, darken in this point right here, this point right here, this one right here, and our origin. We've got a feasibility region that I'm putting in yellow now, and 2 little sections that are kind of outside of that. The reading that you did, I think, mentioned the feasibility regions. You mentioned something about that. It turns out we don't have to look at all the points in the visibility region, or the feasibility region. All we have to do is take a look at the border points. Why am I going to ignore 0, 0? It's a border point. Is that going to help me with anything? No. It's as if the entire science experiment or planting of trees didn't even happen. What's this coordinate?
That is 0.50.
0.50. Down here, we want this one, which would be 70, 0. A lot of people in my other classes are confusing the zeros and the coordinates. Always think to yourself, you move left to right first. So I'm moving over to 0, up to 50. I'm moving over to 70, and then moving nowhere. And neither up or down. What do you think this is? It's hard to tell. What do you think that point is? How many people think it's 30, 30? And how many people have something different? Anybody got anything different?
I mean, I had a different overlap on mine. Mine is about 23, 40.
All right, so there might be some confusion. How do we test whether or not 30, 30 is actually the intersection point, just to make sure?
Calculator.
Plug it into what? Pretend that you are looking at two equations. At some point, I'll have an easel standing that has whiteboard on it. I hate these gray boards. I don't know whoever developed these, but they're horrible to write on. What we're going to do, and where I'd like you to place this, you have some space at the bottom. Put equations instead of inequalities, because we're really interested right now in where two lines are crossing. And you add 600x 900y equals 45,000. Right now, a few people have numbers other than 30 and 30. Maybe those numbers are the correct ones. Let's find out. Think back to last year. How do you solve two equations for two unknowns? What's the most efficient method for doing that with this type of setup? Plug them in. Well, you could do that, but what if none of your answers are right? Maybe your graphs are all wrong. Maybe it's a decimal that we haven't considered. Maybe it won't be whole numbers. How did you do this last year with much simpler coefficients problems? Tim?
You move one variable to the other side.
One variable to the other side. Can you give me a name for the type of method you're talking about? That's one way to do it. I think you're on the right track, but there's a more efficient way to do this.
Hey, are you talking about like elimination?
There we go. You remember elimination? This is the whole reason you do that type of work in Algebra 2, so that you can apply it elsewhere. You have two situations and you're not quite sure where the intersection is. What should I multiply that first equation by? Negative what? How about 20? Negative 20. What will that achieve? What's negative 20 times 30? That's what we wanted. We wanted something opposite one of these numbers. Is this ringing a bell? So I multiplied everything by negative 20, and now I have this equation. This one, I keep the same. That should be negative 42,000, right? Because that's a negative. Negative times that, 42,000. Trying to remember names. Is it not Connor? Is it Connor? Okay. What do I do next with this?
Get rid of the x, since they cancel out.
Effectively, I'm adding two equations. This goes away. What's the name of the method? Elimination. We want to get rid of one of the variables so we can only deal with one variable. Negative 800 and positive 900. 100y. Negative 42,000 and positive 45,000. 3,000. What does y have to be? 30. So it's looking like my 30/30 is correct. Go ahead, take that 30, substitute it back up into the original equation, and verify that x turns out to be 30. Substitute this back into there and verify. So it turns out that if you had a graph and it was slightly off a little bit, the actual intersection is 30/30. You might have to do this occasionally, but most of the time, I'm going to be setting up these graphs with numbers that you'll be able to determine pretty closely what the intersections are. But look for questions. There might be one that shows up on a test where I'll explicitly say, double check your intersection showing elimination method. This is as difficult as the calculation is this year. If you could do this, if you could do something like that, you're gonna be fine. If you can't do this right now, come and see me on a Tuesday or Thursday, we'll do a little review of elimination method. What do I do with these 3 boundary points?
You put them into the carbon dioxide absorption.
Put them into the carbon dioxide equation and see which one gives us a maximum absorption. Which of those 3? And we're looking at x's and y's, x's and y's. We're substituting in what works in this case. What's the best scenario? While you're doing that, I'm going to start writing my final sentence. The city should plant a certain amount of spruce trees and a certain amount of maple trees. What should I be putting in those 2 spots? I'm hearing different results. Who thinks that it's 30-30? Who thinks that it's 70-0? 70-0. If you put 70 into here and 0 into here, that's still going to be more than putting 30 in for X and 30 in for Y. What is your total when you do 650 times 70 plus 0?
45,500.
45,500. And what units is that? What did the 650 and 300 have as units?
Pounds per yard. Yeah.
So we're talking about pounds. And that's our answer. I need this as a final sentence, somewhere below your drawing, above it, to the side. The city should plant 70 spruce trees and 0 maple trees. Give me something that tells me that you understand the numbers that actually came out of your work. This problem was maximization of something. Turn your paper over. We've got a toy manufacturer wants to minimize her cost for producing 2 lines of toy airplanes. I've set up pretty much the same type of graph going by 5s. Do the same thing. And this time, since we're dealing with bats and falcons, I'm going to use B and F instead of X and Y. Just make sure that you label your graph B and F. Yes?
So this was just like the last one, except instead of choosing the highest one, we choose the lowest one.
Correct. The parameters are a little bit different in this one. For the last one, we used money as one of our parameters. Here, money is the minimization equation. So don't assume that money is already always up here. It always depends on what it is that you're looking for. We're looking for cost. So I know down here, let's C equal cost. This time C is representing money. Let B equal number of bats, and let F equal number of falcons. And both of these, the bats and the falcons, are toy airplanes. what will my cost minimization equation look like? If VATS is B and F is Falcons, what money coefficients should I throw in there?
Well, B plus 8Y.
I'm using B and F this time. Just make sure that you choose one of them to be your x-axis and one to be your y-axis. I have B down below, I have F as my y-axis. Parameters. The parameter is a little bit different in this case. There are enough workers to build at least 70 toy airplanes each day. What will that look like as an inequality parameter? Keep the 40 and 60 separate. That's going to be separate parameters. It'll be greater than or equal to, because they're saying the least amount that they're going to produce is 70. It's a little bit unrealistic if that was the only parameter, but then we have some built-in parameters for individual ones, so that will rein it in. Because can workers build infinite toy airplanes? No. And that's kind of what we're saying here with the 70. It's going to be 70 or more. It's just going to be B plus F. Those are the only two things we're making, and that's how many we can make. We're assuming that it's the same amount of energy and work to create a flying bat as it is to build a flying Falcon. This is okay because we now have two separate little inequalities. On the previous page, we had x had to be more than 0 or equal to 0, and y had to be more or equal to 0. Here, we're saying that the bats have to be less than or equal to 40. We're saying that the Falcons have to be less than or equal to 60. By having that in there, it makes sense now. We're not looking at infinite toys. Every problem's a little bit different. The more of these you work on, you'll get an idea of how to deal with them as you read them. So go ahead. Graph B plus F greater than or equal to 70. Graph B less than or equal to 40. How do you graph things that only have one variable? What results? What kinds of lines? Vertical, horizontal. But remember that this one is saying greater than. So where are you going to shade? Above. Where are you going to shade if it's below 40? So I got to move. For B, that'll be to the left. For F, less than 60, that's going to be 60 below. So you get some shading in 3 different directions. Find where they all intersect or overlap, and that'll be your feasibility region. Point out the points that are in that feasibility region. And make a little chart for each one. The same way that you made charts for these inequalities. Work with each other. If you're not sure how to start, or if you're not sure what to shade.
B is for this one, where we end up by using the, can do that,
Yep.
but it'd still give us 71. That's
Right, but you have 070, 70, 0.
Okay.
That's fine. Mhm. Just happens to be a little more symmetrical than the other ones. How would you graph the other ones? Even a couple zeros. The only difference is you don't have any coefficients, it makes it simpler. If I'm making a little XY table for each of these, when you throw in a couple zeros, this is even simpler than the other ones. If that's 0, what's that? And if that's 0, what's that?
70.
So it's very symmetrical. You're going to go up the same distance over here. You're going to go to the right the same distance over here. And it makes for a much nicer line because you're going right through the diagonals of all of these unit squares. Where am I shading? I'm shading this way because I'm looking at greater than. Whenever we have one variable, what I automatically do, sorry about that, that should be B and F, B and F, B and F. This is saying, as far as the line goes, B is always 40. And then you can throw in whatever you want for the other ones. I'll throw in 10 and 20. If I plot those points, 40, 10, 40, 20, I end up getting a vertical line for this one. Where do I shade? Left or right? Left. I'm shading this way. And the other one, they're telling me that F is 60. Well, it's 60 all the time on that line. I can put any numbers I want in for the B part. What does that look like? That looks like 10 and 60 and then 20 and 60. The second number is always 60. So now I've got this. And since I have less than, which way do I shade? Down below. Can you see where all three of them are intersecting?
Yeah, that's fine.
What's the shape? Triangle? So I'm seeing an intersection there, there, and there. It's all coming together within that little feasibility region. Every problem's a little bit different. Depends on your inequalities, depends on your variables. This one looks like it's pretty easy to determine what those points are, though. Wouldn't you say? You don't have to do any sort of elimination method to figure out your intersections. I'm seeing, let's see, right here, what is that, 40, 60? And this one right here looks like 40, 30. And this one? 1060. Before you do any sort of testing now on those points, just look at the points. If I compare these 2 points, which one has larger numbers?
60.
These are the same, and the 60 is bigger than 30. If all you're doing is adding and multiplying, which one of these two is going to give you the bigger amount? 40, 60. Now compare these two. 60 is the same, but 40, is that bigger than 10?
Yeah.
So you know that this has got to be the one that's giving you the maximum. But what do we want in this case? Minimum. I realized that after I circled it. Sorry about that. So test them all out. And that's a frequent mistake. You're going to assume that you're going for a maximum when you're going for a minimum. So maybe it might be a good idea to write that down right underneath your equation. So can we say we've effectively ruled out 4060 as the number?
Yes.
And what is actually being asked for here? It's not asking for the number of trees like the last one. So even though you're determining the number of toys, you're actually your final answer will be just the cost. And what will that C turn out to be? Which one? All right, it'll be 1060. Do we agree with that? Is that better than the 4030? Okay. What do you get when you substitute that in? 600. 600 what? Dollars.
Yeah.
Last thing you should do, the minimum cost each day is $600. Just give me a complete sentence explaining what it is that you found. Some people will write down 600. They have no idea if that's 600 apples, 600 oranges. In this case, $600. Are you getting the hang of this? Is this difficult? You got to watch every little step. You have to make sure that you're interpreting your inequalities correctly. You have to make sure that you're shading in the correct directions. But realize that the problems I'm showing you have some sort of feasibility region. And we are only interested in the boundary points of those feasibility regions. Ms. McClellan is going to stay with you for the rest of the time. I'm going to Baltimore Washington Airport so I can go to Reno, Nevada.